distributed systems from scratch. This is episode 6, Consensus, Paxos. Welcome to season 2. We've spent 5 episodes building vocabulary, partitions, clocks, KP, consistency models. Now we build the algorithms that make distributed systems actually work. And we start with the most fundamental algorithm of all, consensus. Season 1 gave us the theory, what's possible, what's impossible, and what trade offs exist. Season 2 gives us the protocols, the actual algorithms that real systems use. Consensus is the foundation. Almost every distributed system, databases, coordination services, blockchain depends on it. Once you understand consensus, everything else becomes clearer. The consensus problem is deceptively simple to state. How do a group of nodes agree on a single value? This sounds trivial, but remember, nodes can crash, messages can be lost or delayed, there's no shared memory, there's no global clock, and yet the nodes must reach the same decision. Leader election, all nodes must agree on who's in charge. Two leaders means split brain, catastrophic. Log replication, all replicas must agree on the same sequence of operations because the same log means the same state. Atomic commit, all participants in a distributed transaction must agree, commit or abort. Partial commits corrupt data. Let me make this concrete with 3 examples. Leader election. In a database cluster, one node is the primary. It accepts writes. If it dies, the remaining nodes must agree on exactly one new leader. If two nodes both think they're the leader, they'll accept conflicting rights. This is the split brain problem. Replicated log systems like ATCT and Kafka maintain a log of events. Every replica must see the exact same log. If the log diverges, the replicas diverge and the system becomes inconsistent. Atomic commit. A distributed transaction spans multiple nodes. They all need to agree. Do we commit this transaction or do we abort it? A partial commit, where some nodes committed and others didn't, violates data integrity. All 3 problems reduce to consensus. Formally, the consensus problem has 3 requirements. Agreement, all correct nodes decide on the same value, not eventually, not most of them, all of them, the same value. Validity, the decided value was actually proposed by some node. The algorithm can't just make up a value out of nothing. Termination, every correct node eventually reaches a decision. The algorithm can't run forever without deciding. 3 properties, all must hold. Getting all 3 simultaneously is, well, there's a theorem about that. In 1985, Fisher, Lynch, and Peterson proved something devastating. In a purely asynchronous system where you can't distinguish a slow node from a dead one, no deterministic algorithm can guarantee consensus if even a single process can crash. This is the FLP impossibility result. It's as fundamental to distributed systems as the two generals problem, but more formal and more powerful. So, how does anything work? The answer, we relax the assumptions. Real systems use timeouts to detect failures, which technically makes them partially synchronous. Or they use randomization. Or they accept that termination might not be guaranteed in pathological cases but is virtually certain in practice. Paxos takes this last approach. It guarantees safety always and guarantees liveness almost always. Leslie Lamport first described the Paxos algorithm in a 1989 paper called The Part-Time Parliament. It was written as an allegory about ancient Greek legislators on the island of Paxos. The paper was so unusual in its presentation that it was rejected and wasn't published until 1998. In 2001, Lamport wrote a follow-up called Paxos Made Simple. The opening line reads, "The Paxos algorithm, when presented in plain English, is very simple." Narrator voice, it was not, in fact, simple for most people, but we're going to make it simple right now. Here's the setting. A group of nodes needs to agree on a single value. Nodes can crash and recover. Messages can be delayed or lost. But nodes don't lie. We're not dealing with Byzantine faults here. just honest nodes that might be slow or dead. Paxos guarantees if a value is chosen, every node that learns of the decision learns the same value. No two nodes ever learn different values. That's the safety guarantee, and it holds unconditionally, even during partitions, even during failures. Paxos defines three roles. Proposers, they propose values. A proposer says, I think the value should be X and drives the protocol forward. Acceptors, they vote on proposals. A value is chosen when a majority of acceptors accept it. Majority, not all. This is key. Learners, they learn the chosen value. They don't vote. They just need to find out what was decided so they can act on it. In practice, a single physical node usually plays all three roles. The separation is conceptual. It helps us reason about the algorithm. Before we get to the protocol, understand this one idea. It's the core insight that makes Paxos work. Any two majorities overlap in at least one node. If you have five nodes, a majority is three. Take any two groups of three, they must share at least one member. It's a pigeonhole argument. Why does this matter? Because that shared member carries knowledge from one round to the next. If a value was accepted by a majority in one round, any future majority will include at least one node that knows about it. This is the fundamental mechanism behind Paxos' safety guarantee. Look at this visually. Five nodes, N1 through N5. Majority A is N1, N2, N3. Majority B is N3, N4, N5. N3 is in both groups. If majority A accepted value X and a new proposer contacts majority B, N3 will tell them, I already accepted X. The new proposer can't ignore this. It must adopt X. This is why Paxos is safe. Once a value is chosen, the overlapping quorum guarantees it can never be overridden. The protocol has two phases. Phase 1, prepare and promise. The proposer asks acceptors for permission. The acceptors promise to listen. Phase 2, accept and accepted. The proposer asks acceptors to accept a specific value. The acceptors vote. Let's walk through each one in detail. Phase 1, prepare and promise. The proposer picks a proposal number, call it N. This number must be unique and higher than any previous proposal number this proposer has used. In practice, you can use a combination of a counter and the node's ID. The proposer broadcasts prepare N to all acceptors. Each acceptor, on receiving prepare N, does two things. First, it promises not to accept any future proposal with a number less than N. It's saying, you have my attention. I won't agree to anything older than your proposal. Second, it tells the proposer about any value it has already accepted. It says, by the way, I previously accepted value V at proposal number M. Or if it hasn't accepted anything yet, it says, I haven't accepted anything. The acceptor sends this back as a promise message. Phase 2, accept and accepted. If the proposer receives promise responses from a majority of acceptors, it proceeds to phase 2. But here's the crucial part. The value it proposes depends on what it learned in phase 1. If any acceptor reported a previously accepted value, the proposer must use the value with the highest proposal number among those reports. It cannot propose its own value. If no acceptor had accepted anything yet, the proposer is free to propose whatever value it wants. The proposer sends acceptance value to all acceptors. Each acceptor, on receiving accept n value, checks is n greater than or equal to the highest proposal number I promised. If yes, it accepts the value, records it durably, and replies, accepted. If no, if it has since promised a higher number, it rejects the proposal. When a majority of acceptors have accepted, the value is chosen. Consensus is reached. Let me emphasize the critical rule because it's the heart of Paxos' safety. If a proposer learns during phase 1 that an acceptor has already accepted a value, the proposer must adopt that value. It cannot override it with its own. Why? because if that value was accepted by some acceptor, it might have already been chosen by a majority. The proposer can't know for sure, but it can't risk overriding a chosen value. This rule, combined with the majority quorum overlap, is what guarantees that once a value is chosen, no future proposer can choose a different value. Any future majority will include at least one node that accepted the original value, and any future proposer will be forced to adopt it. Let's walk through the happy path with three acceptors. The proposer sends prepare 1 to all three acceptors. A1 and A2 respond quickly with promise 1 nothing. A3 is slow, but that's fine. 2 out of 3 is a majority. The proposer sees no previously accepted values, so it's free to propose its own value. X. It sends accept 1 X to all three. A1 and A2 respond with accepted. Again, A3 is slow, but we have our majority. Value X is chosen. A3 will eventually catch up, but the decision is already final. 2 out of 3 acceptors agreed, and no future proposal can override it. What if the proposer crashes mid protocol? No problem. A new proposer picks a higher proposal number, say 2, and starts a fresh round of phase 1. When it sends prepare to, the acceptors respond with what they've already accepted. If any of them accepted X in the previous round, the new proposer learns about it and adopts X as its own proposal in phase 2. If no value was accepted yet, maybe the original proposer crashed before phase 2. The new proposer is free to propose its own value. This is the beauty of Paxos. No single node is a point of failure. Any proposer can drive the protocol. If one dies, another picks up where it left off. But what if two proposers compete simultaneously? Proposer A sends prepare 1. Proposer B sends prepare 2. The acceptors promise to B, the higher number, and reject A's phase 2 attempt. A retrace with prepare open parenthesis 3 close parenthesis. Now the acceptors promise to A and reject B's phase 2. B retries with prepare open parenthesis 4 close parenthesis, and on and on. This is called live lock. The two proposers keep outbidding each other, and neither ever reaches a majority in phase 2. Paxos' safety guarantee still holds. No conflicting values are ever chosen. But the termination guarantee, liveness, is violated. The algorithm might never decide. The practical solution is to elect a single distinguished proposer, a leader. Only the leader proposes values. This eliminates dueling and is the basis of multi-Paxos. This trade-off between safety and liveness is fundamental. Safety means nothing bad happens. In Paxos, this means two different values are never both chosen. Paxos guarantees safety always, under any combination of crashes, partitions, and message delays. Liveness means something good eventually happens. A value is eventually chosen. Paxos only guarantees this if there's a period of stability where a single leader can complete both phases without being interrupted. Remember FLP. It says you can't have both safety and liveness in an asynchronous system with crashes. Paxos makes the right choice. It never sacrifices safety. It might delay progress, but it will never give you a wrong answer. Basic Paxos, what we've been discussing, decides a single value. That's called single decree Paxos. But real systems need to decide a sequence of values, a log. Multi-Paxos runs a separate instance of Paxos for each slot in the log, but it adds a critical optimization. In basic Paxos, every decision requires two phases, two round trips, expensive. In multi-Paxos, you elect a stable leader. The leader runs phase 1 once, establishing its authority. Then, for each new value, it only needs phase 2, one round trip. This cuts the cost in half. The leader keeps proposing values until it fails or is challenged. When it fails, a new leader runs phase 1 to establish itself, then continues with phase 2 only. This is how most production Paxos implementations actually work. Despite its elegance, Paxos is notoriously hard to implement correctly. The gap between theory and practice is wide. Lamport's paper describes single decree Paxos, but real systems need multi decree. Log compaction, snapshotting, membership changes, adding and removing nodes from the cluster. None of this is specified in the original paper, and getting it right is extremely tricky. The corner cases are vicious. What if the leader fails between phase 1 and phase 2? What about gaps in the log? How do you compact the log without losing safety? Each of these requires careful engineering that goes far beyond the algorithm description. And reasoning about correctness is hard. Google's Chubby team, some of the best distributed systems engineers in the world, reported that despite using Paxos, getting their implementation correct took years of debugging. This difficulty is exactly what motivated the creation of Raft, which we'll cover next. Despite its difficulty, Paxos is deployed everywhere. Google Chubby uses multi-Paxos for its distributed log service, the coordination layer that powers much of Google's infrastructure. Google Spanner uses multi-Paxos per shard for replication, combined with TrueTime for external consistency across continents. Apache Zookeeper uses ZAB, Zookeeper Atomic Broadcast, which is a Paxos variant optimized for primary backup replication. And AWS DynamoDB uses Paxos for metadata consensus and leader election. When you need correctness at scale, Paxos or something very close to it is what you use. In 2014, Diego Ongaro and John Osterhout published the Raft paper with a bold claim. They wrote, Paxos is correct, but it's not understandable enough for building real systems. We designed Raft as an alternative that prioritizes understandability. Raft solves the same problem as Multipaxos, replicated log consensus, but it decomposes the problem differently. Leader election, log replication, and safety are three separate, cleanly defined subproblems. That's our next episode. Let's recap. 1. Consensus means agreement, validity, and termination. It's required for leader election, log replication, and atomic commit. 2. The FLP impossibility says consensus can't be guaranteed with even one crash in a purely asynchronous system. Paxos works around this by guaranteeing safety always and liveness almost always. 3. Paxos uses majority quorums. The overlap between any two majorities carries knowledge forward, ensuring safety. 4. The two phases prepare slash promise, then accept slash accepted. The critical rule the proposer must adopt any previously accepted value. 5. Paxos guarantees safety unconditionally. Liveness requires a stable leader, which is the basis for multi Paxos. Next, Raft. Same problem, cleaner solution. Leader election with randomized timeouts, log replication with simple rules, safety with a clear invariant, explained so well you could implement it yourself. Slide 26, end card, approximately 8 seconds. That's episode 6, Paxos, the foundational consensus algorithm that powers the infrastructure behind the internet. Next time, Raft. Thanks for watching.